Hello, Mr. Bryan here to talk to you about static equilibrium, in this case with torques. As always, with static equilibrium, there's no acceleration. And so before we've had situations like this. Here's an object, there's 5 newtons to the left, 5 newtons to the right, there's no acceleration. Again, 5 newtons to the left, 5 newtons to the right, no acceleration. But if the object is acted on by these two forces, as I've depicted in the last one, even though the net force is 0, you can still have a torque that causes that object to rotate. And so to prevent that, you have to have no net torque. You have to apply the forces so that the net torque is 0. And so that's what we mean by static equilibrium with torques. So not only is the sum of all forces 0, both in the x and the y, but the sum of all torques is 0. You have no linear acceleration and no angular acceleration either. Here's an example. Now there's a lot of information on this particular board, and so I hope that you can see it okay. Imagine that we've got a 1 meter long massless board, and it sits on 2 scales. And there's a person standing on that board, 50 kilogram person, and they're standing a quarter of a meter from one end. So the whole board is 1 meter, and this person's standing a quarter of a meter from one end. And we want to know what's the scale reading on each scale. Now you might guess that the scale reading on the scale that the person is closer to will be larger, and that is true. And we want to be able to calculate exactly how much larger. So what I've done is I've drawn the forces on the board. There's a force from each scale, a normal force, Fn1 and Fn2, and then also the person has weight that pushes the board down. And so there are 3 forces on the board, and we know that the sum of those 3 forces is 0, because that board is not accelerating vertically. So basically, the weight of the person, which is 490 newtons, is equal to those 2 normal forces. But we don't know what normal force each one of them is. We have 2 unknowns. And so what we're going to do then is we're going to apply not only the sum of all forces equals 0, but also the sum of all torques is equal to 0. And so when we try to do that, the first thing that we need to do is choose an axis of rotation. Torques are applied to an axis. And we have a lot of freedom in that. And you'll kind of get the hang of it the more you do. But ideally what you want to do is choose wisely, such that wherever you put the axis, you eliminate a torque that you don't know how to calculate. And so for us, the logical spots would be right here where Fn1 is or where Fn2 is. And I chose Fn1 just because, no particular reason. But I chose that because now that force is acting directly on the axis, it actually doesn't cause the board to rotate. In other words, I've made that r in the torque equation, Rf sine phi, I made the r for that force 0. So this force provides no torque. And then we have a torque provided by the 490 newton person, which tends to rotate the board clockwise. And we have a torque provided by the other normal force, which tends to rotate the board counterclockwise around that blue axis that I drew. So I wrote sigma tau equals 0, and I added the forces. They're all applied at 90 degrees, so I didn't bother writing sine 90. That's 1. I did clockwise as negative and counterclockwise as positive. And so I got the sum of all those torques to be 0. That's the same thing as writing the sum of the clockwise torques have to equal the sum of the counterclockwise torques. So if you want to think about it that way, you can. And that allowed me to eliminate the torque provided by Fn1, and I could solve for Fn2, which turned out to be 367.5 newtons. Now that I know the normal force from the second scale, I can go back and plug that in maybe to my force equation over here and find the normal force from the first one, and that turns out to be 122.5. So the 2 forces from the scales are 370 newtons for the one on the right, and the one on the left is 120 newtons. Let's try one more example. In this example, I have a board that's sitting on 2 sawhorses. This is a long board, it's 3 meters long, it has a mass of 10 kilograms, and it's sitting on 2 sawhorses. One sawhorse is at the very end, and the other one is a meter in from the other end. So 2 meters from the other sawhorse. And we want to find the force that each sawhorse provides to hold up that board. Now, unlike the last one, this board has mass. And so we're going to assume that all that board's mass is located at its center point, at its center of gravity. which would be exactly halfway along its length, so 1.5 meters from each end of the 3-meter long board. And so I've drawn that force here, so 10 times 9.8, 10 kilograms times 9.8 meters per second squared gives us 98 newtons. And then we have the two normal forces from each sawhorse. When I write my sum of all forces equation, I get two unknowns, just like I did in the last example. I get 98 newtons down, that's the weight of the board, is balanced by the normal force from each sawhorse pushing up, but I don't know either one of those. So we'll apply sigma tau equals 0. But first we have to choose an axis of rotation. I can choose any point that I want, but choose wisely. You want to choose a point such that it eliminates a torque that you don't know how to calculate otherwise. So in this case I chose this point right here because I don't know what this force is, and therefore I can't calculate that torque very easily. And so I chose an axis there so that that little r there for that torque is 0. And so when I do that, that's this 0 torque here. And then the sawhorse force from the one on the left is, let's see, 2 meters away, so Fn1 times 2. And then 98 newtons from the center of the board is only half a meter away from this axis. Remember, the center of the board is 1.5 meters, and this is 1 meter in, so this is only half a meter. So I've got that. And I calculate Fn1 turns out to be 49 newtons. I'm sorry, Fn1 is 24.5 newtons. Fn1 times this lever arm is 49. So Fn1 is 24.5. I plug that back into my force equation to find the other force, and I get 74. So it's 25 newtons for the one on the left and 74 newtons for the one on the right. You should practice doing this exact same example, but instead of choosing this as the axis, choose the other sawhorse as the axis and see that you get the same answer. If you can do that on your own, you're going to be able to handle these problems just fine. Thanks for watching.